In times past, when we were faced with an equation in this form, we think to ourselves, well, gee, we need to put this into the form of a function, which means we need to solve this for y. So we would go through and we'd say, okay, I'll add 4y on both sides, giving us this, and then I'll divide through by 4. So divide this by 4, divide that by 4, we get all of this business. Now we can easily take the derivative, y prime then is 3 over 2x squared. Well, it'll turn out that we aren't always able to rewrite the equation into this form. Sometimes equations come at us and we can't really put it into this form at all. But it doesn't mean we can't look at derivative. There is a derivative process, and that's what we want to look at in this section. It's called differentiating implicitly, or implicit differentiation. Now, the implicit idea is this, that although we have a y as a function of x here, this is the explicit way of writing y as a function of x. This is y as a function of x implied or implicitly. So this is the implicit form of the function. This is the explicit form of the function. And when we differentiate implicitly, it means we are differentiating in the implicit form of our function or our equation. So let's go through the process. It'll turn out now that it's very similar to the processes that we talked about earlier. We're just taking every term and we're going to differentiate as we did before, except we have to indicate at times that we are performing a dy over dx, a derivative of y in terms of x or with respect to x, when we're not actually doing that. We indicate that we are, even though an x doesn't appear. Here's what I'm talking about. An example goes a long way to understand this. The derivative here is 0. Here the derivative is 3 times 2, 6x squared as usual. Now for this one, we think, let's use the chain rule here. You see, let's jump in here and replace y with x, and what would it be? Well, it would just be -4. Now let's indicate that it was a y in here and not an x. You see, we actually performed this operation. It was a derivative of y with respect to x, so it was a dy over dx, and we put that indicator in here as a clue of what we have done. And that's kind of an important indicator. And then the derivative here would be 0. Now, the dy over dx, there are a couple of notations. This is one notation. The other notation is just to put it in as a y prime. And the y prime is a little easier to manipulate at times. So I'll use the y prime here. Now, if we're going to solve this for y prime, and we want to do that, we'll add 4y prime on both sides. We get 4y prime then is 6x squared, and y prime then, y prime then is 6x squared over 4, and reducing, y prime is 3x squared over 2. And notice, 3x squared over 2, 3x squared over 2, we would expect them to be the same. So finding derivative implicitly and finding the derivative explicitly actually turn out to be the same thing. And sometimes it's necessary for us to use the implicit form, as is true in this next problem. Here we have an equation. Now notice that there are 3 terms involving y. It would be very difficult here to try to solve this equation for y. So if we want to find the derivative, then we'll perform that operation implicitly. That is, we'll go through every term and perform a differentiation. All we're doing is saying we're going to take the derivative of this side, we're going to take the derivative of this side. And that's the indicator here. Now let's just march through and do it. So we're saying, what's the derivative of this term? Well, it's 3y squared, but I'm doing it as a dy over dx, and I indicate that like this. You see in here, same idea. This is 2y, y prime. This is -5, y prime. This is the normal way. 2 times the -1 is -2x, and on the right, 0. All right, now our task would be to solve for y prime. Well, these 3 terms have y primes in them, so I'll snag those out as a common factor. I've got 3y squared plus 2y minus 5. And on the right, and I'm going to kick this over in the same step, this is 2x on the right side. So now I can solve for y prime as 2x on the right over this trinomial, 3y squared plus 2y minus 5. Now notice that the derivative here has both x and y variables within it. And that's not a big problem, though. We can still answer questions such as what's the slope of the tangent line at a point and such things as that. We just have to use this expression with both x's and y's contained within it. Incidentally, the graph of this equation looks like this. Notice that this is not a graph which tells us that we have y as a function of x. It fails the vertical line test here. But nonetheless, we have a relationship between x and y. We can put that relationship onto a graph. We can examine the situation about slope of tangent line. And let's do that. If we want to find the slope of the tangent line at these 3 points, you see, then we just go through and put the information about the 3 points into the derivative, just as we have done so many other times with other kinds of equations. Now, by the way, constructing this graph was no big deal. I want to just show you that, that in circumstances like this, you resort to the most primitive form of what you understand about graphing, and that would be the point plotting method. And here it would be pretty easy to make a table of values and plot some points. Now, to make the table of values, you might notice in our original equation that we have a lot of terms involving y. So it's easier to plug in y values and then solve for x. If y is 0, for example, if y is 0, then these 3 terms go out and we have negative x squared equals negative 4, or x squared is 4, or x is plus or minus the square root of 4, or x is plus or minus 2. So plus or minus 2. And that gives us a couple of points to plot. The point 2, 0 is here, and the point negative 2, 0 is here. And away we go with other points in the same way. Okay. Well, let's get back to the problem at hand and talk about the slope of the tangent line at those points. Now, for each one of them, we're going to plug in the information from their coordinates into the derivative. And as we go, we would like to have a look at what we might expect for the slope of the tangent line. The first one at 2, 0, 2, 0 is this point. Looks like it's a negative slope, and it looks like it's kind of right around negative 1, but maybe a little bit different than negative 1, but pretty close to that. So we know what pretty much to expect. So for the point 2, 0, we are replacing x with 2 and y with 0. So when x is replaced with 2, we have 2 times 2, 4 in the numerator. And in the denominator, if y is 0, these terms go out and we have negative 5. So this becomes negative 4/5 then for the slope. Okay, that's about what we expected. A negative slope right around negative 1. That's right around negative 1. For the next point, let's see, the next point is 1, 1. And let's look at the graph and see what we might expect for that. The point 1, 1 is here. Oh, the slope of the tangent line. Gee, it looks like the tangent line, gee, it could be a vertical line. But you remember that the slope of a vertical line is undefined. Let's see if it doesn't turn out to be undefined over here. Let's see, for the point 1, 1, if x is 1, we have 2 times 1, 2 for the numerator. In the denominator, we have 3 times 1 squared is 1 squared is 1, so 3 times 1, 3. And then plus 2, that's 5. 5 minus 5, oh, that's 0. 2 over 0, that is undefined. Next point is 1, negative 3. So for 1, negative 3, we'll plug in a minute. Let's look at what we might expect. The 1, negative 3 is here, and that tangent line looks like it's going to go like this. So it's going to have a very small positive number as its slope. All right, let's see if we get that small positive number. If x is 1, we have 2 times 1, or 2. And if y is negative 3, oh, here we go. Negative 3 squared would be 9. 9 times 3, 27. And then 2 times negative 3 is negative 6. So this is minus 6. And then bring down the minus 5. Well, let's see. The minus 6 minus 5, that's minus 11. 27 minus 11 is 16. So we have 2 over 16, or 1/8 for the slope of the tangent line at that point. Let's take a look at another one. This one says, find the slope of the tangent line to the graph of this equation at this point. Now, all we need to do to find the slope of the tangent line at a point is to find a derivative and then plug in the information into the derivative. That's all there is to it. And we can decide whether or not we want to treat this problem implicitly or explicitly. If we want an explicit kind of equation, then it would require that we solve this for y. It turns out we can do that in this particular problem. I want to show both methods. I want to show you both ways of doing business here. The first way, let's go ahead and do it implicitly, the way that we might be expected to do it in this section. So implicitly, we would get right to the matter of differentiation. And differentiating implicitly means we just attack every term. Attacking this term, we would get 2x. And the derivative here, 2 times 4, 8y. But we have to indicate that we're talking about a dy over dx, or a y prime here, and then on the right, 0. So let's see, we have 8y y prime equals negative 2x. And dividing on both sides by 8y, we find y prime to be negative 2x over 8y, or negative x over 4y. All right, very good. Now, for this particular point, and incidentally, the graph of this is an ellipse. You can see that it takes the form, the equation takes the form of the ellipse when you divide through by 4. You see, we would have x squared over 4 plus y squared over understood 1 equals 1, and we're accustomed to dealing with that very quickly. We know that we have this a and b involved in it and so on and so forth. But at any rate, the graph looks like this. And let me talk just a moment about the nature of this point and what we might expect for slope. The square root of 2, let's see, out to the right, the square root of 2, that's a little more than 1, a little less than 2. All right? And negative 1 over the square root of 2 just pops that value onto the graph, roughly in this position, so the slope of the tangent line will be a small positive number. That's what we're expecting anyway. Let's see what we get. If we're going to throw this information into that derivative, so we'll have, let's see, for the point root 2 negative 1 over root 2, this becomes negative root 2 for x, and then 4 times the y value, but the y is minus 1 over root 2. Looks a little convoluted, doesn't it? We might have a little algebra to do on this. This fraction flips over, and the square root of 2 becomes a factor in the numerator. The 2 minus signs gives us a plus. And if the root 2 is in the numerator, we have the square root of 4, which is 2. And in the denominator, we still have this 4. So it's 2/4 or 1/2 for the slope of that tangent line. Now, I mentioned earlier that we could deal with this problem explicitly. That is, we could redefine the equation. Let's go through that process and just see what it looks like. Occasionally, you might verify things both ways. You know, I don't want to erase all of this. I want to leave this y prime here if I can, just to refer back to in a little bit. This was our y prime right here. It's right in the way, but let me see if I can work around a little bit. I want to solve for y, so I've got 4y squared equals 4 minus x squared. Then I'll divide through by 4. I've got y squared then is 1 minus 1/4 x squared, and I am in a little trouble here. Let me just make a note of it out here, that y prime I found earlier to be negative x over 4y. Okay. And from here, y is plus or minus the square root of 1 minus 1/4 x squared. Now this really represents two equations, doesn't it, or two functions. One of the functions is y equals, well, you can see what they are, y equals plus this and y equals minus this. You see, those are the two functions. And if I were defining this situation in terms of two differentiable functions, I would write each of those functions separately. And if I want the interval over which they're differentiable, then it would be the interval from, let's look over at the graph, you see, from this point to that point, but not including the endpoints. The endpoints of the interval would not be differentiable, so I would say that we're differentiable from -2 is less than x is less than 2, if I want to be very formal about that situation. Now, from this point, I could find y prime. Let's see, I've got y prime is, now I'm thinking of this, let me burn a step and change the form just a little bit. And I'm not sure I want to do this with a plus and minus in it. I might want to do just one of them, but let me take a shot at it with the plus and minus and see if we don't, if we're going to get in trouble. Y is plus or minus 1 minus 1/4 x squared to the 1/2 power. And now I'm going to use the chain rule, and y prime then is plus or minus 1/2. Now I'm thinking 1/2 times single entity to an exponent 1/2 minus 1, which is minus 1/2, times the derivative of the single entity. So the derivative here would be -1/4 times 2. That's -1/2 x. So -1/2 x. And now we have to clean all of this stuff up. Are you starting to see the value? I'm hoping that you're starting to see the value of deriving this or finding the derivative implicitly, because the explicit form of this is much more convoluted than the implicit form. And I'll go through and finish. What I aim to show is that this is the same as that. You see, that we get the same thing regardless of how we go through this. And there's a little trick in here that I'll show you in a second. All right, let's see. We're talking about a negative exponent here. We're talking about a radical for this and a denominator. We're talking about plus or minus 1/2 times the minus. So we have plus or minus times minus causes this to become minus plus. And then in the numerator, we have this business in the numerator. So it's 1/4 x. And then in the denominator, we have this stuff, the square root of this binomial. So we have the square root of 1 minus 1/4 x squared. Now, I'll tell you how, now we're trying to make these two look alike, and I'll tell you how the manipulation is going to go. We are referring back to our form right here, and we'd like to find this form somewhere in our problem so that we can substitute y for it, you see. And I'm seeing that we're just about right there now. We're close. I've got this rascal, pretty close to this rascal in the denominator. Only thing is, I've got a plus minus here, but I don't have anything right here. However, what I can do is this. I'm thinking that, gee, you know, we can swap signs in a fraction like this. That is, having minus plus in the numerator and having minus plus in the denominator, I can just swap those two. It's kind of like having, if I had plus up here and minus right here, I could swap those two and have minus in the numerator and plus in the denominator. Now, the tricky thing about that in dealing with the double sign situation is this. Let me go ahead and make the swap. Okay, now I made the swap. Now what I want this to read though is not minus plus, but plus minus. And to get that situation to change, I need to multiply in both numerator and denominator by -1. So I'm thinking about, okay, I'll multiply -1 in the numerator, -1 in the denominator. And now the numerator becomes negative and this becomes plus minus. All right, let me work up. See where I have some room. I'm going to work up toward this way. So I have -1/4 x in the numerator. In the denominator, I have plus or minus the square root of 1 minus 1/4 x squared. And now this plus or minus 1 minus 1/4 x squared, that is nothing but, that's nothing but this. So this denominator is nothing but y. Okay, good. I've got -1/4 in the numerator x over y, and multiplying by 4/4, it turns out that I get -x over 4y, just like that up here. So with an awful lot of manipulation, we could deal with the situation explicitly, but it was a whale of a lot easier if we deal with it implicitly. Let's go through the implicit-explicit differentiation again on this problem. Now notice the large number of terms here. Notice that this term and this term involve y. When we go through the process of trying to solve this for y, we want to kind of gather the terms involving y together and try to create a factorization opportunity. It's kind of like putting the equation into the standard form for the equation of a circle whose center is not at the origin, which is exactly what this is, incidentally. Okay, so we would rewrite as x squared minus 4x. Put the x terms near one another, then leave a little space, put the y terms near one another, take the constant, kick it to the other side. We're setting ourselves up to complete the square. Now, completing the square here, you see we're thinking of the problem like this. You see, completing the square, completing the trinomial square, remember half of this squared would be 4, so I'm adding 4 here. If I add 4 on the left side, I got to add 4 on the right side. And then same idea here with the y's. I leave a little space over here, and I'm completing the square. Half of 6 is 3, 3 squared is 9, so I'm adding 9 here, but if I add 9 here, I have to add 9 on the other side. And now I am able to factor. Factoring this trinomial, I get x minus 2 squared. Factoring here, I get y plus 3 squared. And on the right, the 9's take each other out, and we have 4. And now I'm pretty much ready to go. It's at this point, though, in the problem where I could construct a graph. And I've constructed the graph here. It's the graph of a circle. The center of the circle is at 2, -3, and the radius of the circle is 2. And we can see through all of that by looking at this form of the equation. So here's the graph. We're not going to refer to it that much in this problem. We're going to perform the differentiation. We're not going to actually find slopes of tangent lines here. I'm sure we can do that. But I want to show you the algebra involved in the explicit form. That's what's so challenging here. We simply want to verify that the derivative of the explicit form and the derivative in the implicit form are the same. And there are some challenges in the algebra here, and we saw those challenges earlier on the previous problem. But the first step is to solve this for y. And to do that, we'll take the term involving y and isolate it first. And we do that by subtracting this binomial squared on both sides. So we'll have 4 minus x minus 2 squared on the right. Now, let's see. We want to solve this for y, so we want to clear the exponent by the square root property. Then this binomial is plus or minus the square root of this side. And then subtracting 3 on both sides, we get this. Now we have solved this for y. And now we're just about ready to go through the process of finding the derivative. It's important that we rewrite a little bit. It's easier if we rewrite this in a parenthesis here. Think about all of this as being to the 1/2 power. So when I rewrite upstairs over here, there'll be a bracket here, and this will be to the 1/2 power. Let's go up here. So -3 plus or minus bracket, all of this to the 1/2 power. Now we're ready to go with the derivative. Now, the derivative of the 3 is out of here, so we're talking plus or minus. Now I'm using the chain rule here, so I'm thinking of this as a single entity. So 1/2 times single entity, 1/2 is plus or minus, 1/2 times single entity to an exponent which is 1 less than this. 1/2 minus 1 is -1/2. Then times the derivative of the single entity. Well, the derivative of this, the 4 goes out. Let's see, the derivative of that part. Again, I'm using the chain rule. So I'm nesting the chain rule within this problem. I'm going to use the chain rule again right in here, single entity. So I have -2 times single entity, -2 times single entity, times the derivative of the single entity. The derivative of the single entity would be just the 1. So now I'm on my way to cleaning up. Well, let's see. In the numerator part, I have, now by numerator part, I'm thinking, okay, I got a negative exponent, so this part, this factor, is going to move down to the denominator. And so I'm not even going to consider this right at the moment. So I'm considering the plus or minus 1/2 times -2. Let's deal with that right now. So we have plus or minus times minus. You see, that changes this to the minus plus situation. 1/2 times 2, that's 1. Okay, so they're out of here. And now I have only the x minus 2 factor. Boom, there we are. And this comes down to the denominator, and we have, and since it's an exponent of 1/2, it's the square root of all of that. So the square root of 4 minus x minus 2 squared. Now, at this point, you might think, well, gee, we're in relatively simple form. Let's just leave it alone. Let's just leave it right here. Well, okay, that's true. We are in relatively simple form. But we want to try to write this in a way that will relate to the implicit form. And you might be thinking, well, how do we know what relates to the implicit form until we do the implicit form? Okay, we can go over and do the implicit form right now. Let's go do that. Here we go. And we'll find that it's a good deal easier. So we have x squared plus y squared, and here's our original equation. Implicitly, this becomes 2x. Implicitly, this is 2y, y prime. Implicitly, this is -4, just the regular way. Implicitly, this is 6, but the y prime has to be tacked on. This goes out. All right, now all we have to do is solve for y prime. So we'll put the terms with y prime in them next to one another. Now notice I'm factoring as I go. I'm taking y prime out of these two terms, and I'm left with 2y plus 6. So y prime times 2y plus 6. And I'm taking these two terms and kicking to the other side. So I subtract 2x, and I add 4 on both sides to accomplish that. Now I'm dividing on both sides by the coefficient of the y prime, and so I have this, and again I'm factoring as I go. The 2 comes out of this binomial giving me this, and I'm factoring here -2. I'm pulling -2 out of these two terms, so I get x minus 2. Now the 2's go out, and I have this. Okay, here's our implicit differentiation. And notice the appearance of y in this denominator. That's the key factor. When you're trying to make the explicit form and the implicit form look like one another and show that they are like one another, it brings back the memories of dealing with identities in trigonometry, I'm sure. But we have to deal with that y. Now let's come back over here and talk about where we were before. We were at this point in the explicit form. And I've got to get a y in here somehow. And the way that you do that is you find a circumstance in this that gives you the y from some previous step. Now, here's a y up here, but let's come down here. Here's a y. Now, notice that it's -3 plus or minus the square root of all of that business. Well, gee, we have in that denominator the square root of the business. Here's the square root of all the business. All right, but we don't have plus or minus, we don't have the -3, but we can manipulate to that point. Now, the first thing I'd like to do is deal with this plus, minus, minus, plus stuff. And it's just a little, it's an algebra trick, I guess you'd say, but it's just good algebra. All we're doing is this. Now, to get these signs to flip, I have to multiply in this numerator by -1. So if I multiply by -1 over -1, then this would become plus minus. All right? whoops, and this would become negative. Now at that point, when this becomes plus minus and that's negative, at that point I can just swap these. I'm swapping the sign. There's a single item in the numerator, single factor in the denominator, so I'm just swapping those items. So I'm taking this plus minus and swapping it with the minus. And now that's how I get to this point. So it was a little double whammy there to arrive at this point. Now you might be saying, well, how do we get the 3 in there? We need a negative 3 plus or minus all this business to replace for y. Well, I can do that pretty easily. I can just say, all right, I'm going to pop in a negative 3 here if I put in a plus 3 out here. You see, minus 3 plus 3, they would take each other out under normal conditions, but I'm just creating a circumstance where I can make a substitution for y. So I'm creating the expression for y right here, so I replace this expression with y, and in the denominator then I have y plus 3. So I have the same situation that I had over here in the implicit form. I think you'll agree about right now that the implicit version of differentiation is a real handy tool to have available to us. In this problem, let's find the second derivative of this equation, second derivative. Now we're going to do this implicitly, and we are going to look for some opportunities to simplify by back substitution. Let's go through it, and you'll see what I'm talking about. Implicitly, the derivative here would be 2x. Here it would be negative 2y, y prime, and the derivative of 16 is 0. Now remember, the y prime here is just a tack-on. You can think of it as just a tack-on situation to let the audience or the viewer or let yourself know that you are finding the derivative of x in terms of y, even though there was no x in the item to begin with. That's why the y prime needs to make its appearance. All right, now we'd like to solve this for y prime. So we'll kick 2x to the other side, subtracting 2x on both sides, and then divide on both sides by negative 2y. So y prime is this, and the 2's go out, and the negatives go out, so we have y prime is x over y. Now we're ready to go, and see, this is the first step. The first step is to find y prime. Now we want to find y double prime. So we want to take the derivative of all of this. Okay. To do that, it's a little easier instead of using the quotient rule, and there are several attacks here. One attack, a way of doing it, is to multiply on both sides by y to clear this denominator. I just decided to do that on my own because it's your choice how you want to attack it. I chose to attack it this way. All right, so we have y prime equals x, and now by the product rule, I'm thinking y times the derivative of y prime. Well, the derivative of y prime is just 1. I mean, think about, see, it doesn't make any difference. If you're dealing with a letter other than x, then you always tack on, you use the basic rules and then tack on the kind of derivative that you're talking about. And here, the letter is this. The letter is y prime. Well, what is the derivative of that? A single letter, whether it's T or R or M. You see, if it's just a single letter, it's 1. So it's just 1, and now we tack on the derivative that we're taking. Well, we're in the second derivative point right here. So it's d2x over d2y is what we're indicating here, or y double prime. And then the other part of it, remember, it was y times the derivative of this, and then it's this times the derivative of y. Well, the derivative of y is 1, but we have to tack on the y prime, you see, factor. So y prime here. Now we have an opportunity for substitution. Y prime we found earlier to be this fraction x over y. So each of these factors is x over y, x over y, x over y. Oh, and incidentally, I almost left out the derivative of the x was 1 on the right side. Okay, x over y, that's x squared over y squared, and we're going to kick that x squared over y squared to the right side in the next step. So y double prime is 1 minus x squared over y squared. Now, what I'm trying to do at this point is to isolate the y double prime because I'm trying to find y double prime in this problem. That's the whole object. So let's see, y double prime then is, I'm dividing through by y, so this becomes 1 over y, and then x squared over y cubed. And now I'd like to bring these terms together, and I can do that by thinking of y squared over y squared here. So this would be y squared over y cubed. And then the denominators are alike, so I have y squared minus x squared in the numerator. And now I'm going to go through some creative substitution, because what I need to recognize at this point and at some point, I need to come back and look at some opportunities for consolidation. And I have a good opportunity right here. X squared minus y squared was 16. So if I can cause this y squared minus x squared to look like an x squared minus y squared, then I can substitute in there and make it 16. And I can do that by forcing the factorization of -1. Forcing negative out of these two, this becomes minus y squared plus x squared, or x squared minus y squared. Just flip them around when you factor out the -1. All right, and now this x squared minus y squared is 16 from above, and so it's -16 over y cubed for the second derivative of this equation. Using implicit differentiation, in an equation we can differentiate with respect to x, with respect to y, or with respect to a letter that doesn't even appear in the equation. Take a look at this equation, and let's first differentiate with respect to x. Now this is the differentiation that we have been doing all along. So implicitly now with respect to x, it would be, let's see, the derivative of x squared is 2x, and the derivative here, we have to use our product rule, and I'm thinking, okay, plus, and I'm putting a bracket. There are several ways to do this correctly. Putting a bracket here, and I'm thinking of this as one factor and this is the other factor. So it would be minus 3x times the derivative of y squared. So it's 2y, y prime. Now remember, y prime, if we're talking about with respect to x, this is dy over dx. That's what that y prime means. All right, so we have this. And now the other part of the product rule means take the y squared times the derivative of this. So it's y squared times the derivative of minus 3x would be minus 3. And then let's march along. The derivative here would be 3y squared times the y prime again, and the derivative of 10 is 0. Okay, let's clean up a bit. And actually what we're aiming to do now in the cleanup process, we want to come down to a point where we have y prime equals eventually. So that's our goal here. Let's see, what have I done? I've got negative 3x times 2y, y prime. Negative 3 times 2 is negative 6, x, y prime. All right, then here I have negative 3y squared, so negative 3y squared. And then bringing this down. Now I'd like to isolate the terms involving y prime. These two terms involve y prime. I'm writing this one, the positive one, first when I bring down. So I'm writing this one here, and I write this one here. Now I'm kicking the other two terms to the other side. The minus 3y squared, add 3y squared on both sides, plus 2x, subtract 2x on both sides to get this. All right, now I'm factoring the y prime out of these two terms. When I snag y prime out, I'm left with 3y squared minus 6xy. And on the right, I have the binomial. Now I divide on both sides by this binomial, and I get this. Okay, so that's implicit differentiation with respect to x. Let's take the same equation and differentiate with respect to t. With respect to t, a letter that doesn't even appear in the equation. But that's not a big problem, because all we have to do is just put in the correct notation. We're thinking about differentiate here, it would be 2x. Now with respect to t means we have to add a dx dt. Now we're differentiating x with respect to t in this particular part of the problem. You see, and that's what we're indicating right here. And now in the next part, we're using the product rule again. And again, I'm thinking negative 3x times y squared. And this time I'm not using a bracket, no big deal. I have negative 3x times the derivative of this part. So negative 3x times the derivative of this would be 2y but it's a dy over dt. It's the derivative of y with respect to t. You see, and here's a situation. In this problem, it's very important that we use this fraction notation rather than the prime notation. T prime, you see, would not do the trick here, because in some situations we have a dy dt, and in other situations we have a dx dt. So we have to use that, this designation to know exactly what we have involved. All right, then going on, let's say I did the first part of the product rule right here. The second part is the y squared times the derivative of that. So it's y squared times the derivative of this is -3. But again, it's the derivative of x in terms of t, or with respect to t. And then in the next part, the y cubed is 3y squared, and then it's a dy over dt. And now, just to clean this up, we're going to put the dy dt's on one side of the equation and the dx dt's on the other side, and tidy things up quite a bit. All right, let's see. I'm putting the dx dt's on the left side. Here's a dx dt, and here's a dx dt. So I have 2x dx dt, and then minus 3y squared dx dt. So minus 3y squared dx dt. And then on the other side, I'm throwing the other two terms to the other side. That's this term and this term. This is -6xy dy dt. And on the other side, it becomes positive 6xy dy dt. And over here, we have 3y squared dy dt. On the other side, minus 3y squared dy dt. And now, it's kind of a good idea to further clean up, to complete the house cleaning. We'll factor the dx dt from these two terms, and I'll put the common factor over on the right side, which is typically where it goes. So 2x minus 3y, oops, I need a squared here, dx dt. And on the right side, I'm factoring out the dy dt, and I'm putting that on the right side. It's 6xy minus 3y squared dy dt. We'll see how this comes in handy in the next section.